uncertainty, what is that, and is it a problem? So starting then with the big picture on why we need carbon storage in biochar and other methods for carbon dioxide removal. Well, it's that if we want to reach the climate targets of staying below 2 degrees, we need to reduce emissions fast. And for that, any emission reductions or carbon dioxide removal is contributing. So that is where we are now. Carbon dioxide removal contributes to climate change mitigation. But looking forward some decades to later parts of the century, we need to get down to zero, net zero. And it's not going to be that we don't have any CO2 emissions, which means that we will also need negative emissions. And that's where carbon dioxide removal is needed, and biochar and other technologies have a special role. And beyond that 0 point, we will need to have net negative emissions to reduce the concentration of carbon dioxide in the atmosphere, which means there's a need for large amounts of carbon dioxide removal technologies. So depending on where we are on this scale, there will be slightly different roles for the carbon storage in the large climate change picture. And when we look at biochar specifically then, biochar systems contribute to climate change mitigation through the carbon storage, but also in other ways, through soil effects, affecting the emissions from soils, through substitutions when other emissions are avoided because we are using biochar instead. But there are also emissions from the supply chain. So this in total gives the full life cycle climate impact of biochar. And when we look at life cycle assessments that have been performed, we see that the carbon storage or carbon sequestration is a large part of the total climate impact, and it also has large uncertainty. And that's why we still need research on understanding this carbon storage, and that's why I'm interested in this. I come from the life cycle assessment, so looking at those full climate mitigation impacts, but then realized that we would really like to know more about the carbon storage. So asking then questions about how much and for how long is carbon dioxide removed with biochar. And what is it that happens with biochar in soils? When biochar is placed in soil, there will be interactions then between the soil and the biochar. And it's those two factors, the surrounding environment and the characteristics of the biochar, that will determine what happens and how persistent the biochar is. And biochar, like other material in soil, is decomposed by microorganisms. And we know that the most persistent fractions of the biochar decomposes very slowly or not at all. And the biochar characteristics, they depend both on what feedstock material that the biochar was produced from and the production process, how the biochar has been produced. And there, temperature is a key factor. I will go a little bit more into detail on these things as we continue here. But first, I'd like to say some words about our research project. We aim at supporting transparent and reliable biochar carbon removal. We are doing incubations and field experiments with a Nordic focus. You can see here to the right, it's our postdoc, Hai Chao Li, who is doing most of the work with these experiments. And then we have been revisiting the existing literature with incubation data in focus. And I'll come back more to what incubations are, but this is this laboratory investigation of decomposition of biochar. We also have had and continue to have dialogues with researchers and stakeholders to understand better and what is needed and to try to convey the scientific state of the art. So this seminar today is also part of that process. And then we've published guidelines. And this is in two parts. What we've done already is guidelines to be able to say what can be recommended already today based on the current state of the art. And then towards the end of the project, we will revise this and come back to what can be recommended based on findings and state of the art then. This is because we know there's a great interest in this topic and we didn't want to wait until the end of our project to say something, but rather try to convey clear messages and the state of the art at this stage in the middle of the project. So what mechanisms is it that makes biochar a durable carbon storage? It's what happens during pyrolysis of biomass that the organic matter is converted from lignin, cellulose, and other substances into fused aromatic structures. But then it's also things that happen later in the soil. Biochar particles are disintegrated, but they also move into deeper soil layers and sediments, potentially. And what we know about this air environment is that there is less biological activity, so it can be expected that the biochar is even more durable there. And another third factor is that the biochar reacts or is physically, also not just chemically, adsorbed to soil particles, organic matter in the soil, and this can become a protection mechanism so that the biochar as such is not accessed by microorganisms, and then also increases the durability of the carbon storage. Biochars are different. It's not just the same black carbonized material. And key factor that determines this is the pyrolysis temperature that has been reached. And that means that we can also use the pyrolysis temperature as an indicator of how aromatic is the biochar and how persistent is it. We know that higher temperatures indicate higher persistence, but there are other factors that are important that are related to heat, like residence time at this highest temperature, the rate of heating, and then also the biomass quality. And in a laboratory, when you are making small amounts of biochar, it can be quite easy to measure exactly the temperature. But when you're in a larger production, to know precisely how the temperature is inside the reactor and for each particle is not possible and has turned out to be rather difficult. Another negative aspect with temperature as the measurement is that you have to be there when biochar is produced. This is not something that you can measure on a sample afterwards. So another indicator that has been widely used is the ratio between hydrogen and carbon in biochar samples. Lower hydrogen-carbon ratio indicates higher aromaticity and higher persistence then. This is something that is well-established measurements, and you can measure it on a sample after production. Its most negative is that it's a bulk metric on the full sample, so you do not see the heterogeneity within a biochar sample. And that's why there is an interest in other chemical structure analysis and test, because it can tell us more about the actual chemical structure of a biochar sample. And there's a range of different methods that have been used in research. And last one here, reflectance, has been used in interesting research recently. And this shows that biochar samples are heterogeneous, as I said, and it also links to characteristics or categories of organic matter that are well defined and well known in geology. These have previously not been used in biochar research, but there's a great opportunity for this to help us understand biochar by drawing parallels from organic matter in geological layers. One important part there is that it's shown that high temperature biochars contain a large fraction of inertinite, which is the most stable form of organic carbon. And this picture I have from the European Biochar Industry Consortium, who have been looking into this research as well as our research, and recently published a report on their view on the state of biochar permanence. And this research is from the research group of Hamed Sanai at Aarhus University in Denmark. So for estimating biochar persistence, different approaches have been used. And the most established, which I will talk most about continuing from here, is the biochar decomposition experiments. So doing experiments with biochar decomposing in soils. Other methods that add to knowledge about biochar persistence and have Other strengths and limitation are these methods, as I just described, that look at molecular structure and how biochars are resistant to thermochemical, so heating and chemical exposure. There's also research on global carbon budgets of bushfire char, also called pyrogenic char, that can give us some understanding of what happens with biochar in the long term. And then analysis of archaeological remains of charcoal also can add, and together these things can give us a fuller picture, but this also then requires combining knowledge from quite different fields of research. And then going into decomposition experiments. We see clearly that biochar decomposes much slower than fresh original biomass over measured time. You can see here time for these measurements are about 2 years, 1 to 2 years. In fresh biomass, about a third is gone after 1 year. But if it's char from pyrolysis, it's a completely different picture. With higher temperatures, and these are not super high, but 300-400 degrees and upwards, most of the carbon is still remaining after a year. So it's really been stabilized through pyrolysis. And we find chars from hydrothermal carbonization and low temperature pyrolysis that have been exposed to less than 300 degrees. We find in between here. So this is showing us that also that soil organic matter that is produced from the decomposition of fresh biomass is quite different from biochar carbon. We cannot use soil organic matter as a proxy, but rather biochar is very different. So incubation experiments. We are doing new such experiments in our research, but what we've already done is a reanalysis of published incubation experiments. So biochar is placed in soils and the carbon dioxide evolution over time is measured. This can be done in small samples in a lab or in bigger columns in labs or even outdoors for getting more realistic environments. And the curve here to the right, we see one of these experiments, and here we have a bit of up and down. That's what we see when we have seasonal variation, so exposure to different temperatures with the seasons. Also see here clearly that there is fast decomposition in the first few months and then slower, and then after some years it's even slower. So this also shows that there are variation. There are some substances in the biochar that are easily degraded by microorganisms, but when they are gone, much less happens and the biochar remains much more the same. So what we've done is to reanalyze the published incubation experiments, taking the data from such curves that I showed on the previous page, and each such curve ending up as data for one observation, and then compiling many of such data sets from the scientific literature and analyzing them, extrapolating from these few years of experiments into what can we expect happen in decades or up to 100 years. Correlating this to the biochar quality and other experimental factors to create biochar stability models. And then also, and that's how far we went in the scientific paper that we have published, which is available and it's openly available. And what I will present today also includes this final part of making adjustments for policy and so that we can have a biochar stability model for a given policy use. And I should also say that what we have done, the data and the modeling is all available also as open source code, and that's also to enable future update with new experimental data sets that they should be easily possible to include in future modeling. So I should also say that it's my colleague Elias Assi who did most of this work. So even though I say we, most of the he's the one who's credited for most of the work. Yes, a number of observations of individual decay curves of biochars and lots of different characteristics of the biochars and the experimental settings were found in these published data sets. But we also still see that there are key data gaps. Most of these incubations have been made with rather low pyrolysis temperature compared to what is done in commercial biochar production. There's not much above 600 degrees. And also low HC ratios are also not seen in this data set to a large enough extent. And soil temperatures have mainly been 20-25 degrees. There are some trials at higher degrees. But for our climate in the Nordic countries, we're interested in colder temperatures. So that is something that we are doing in our incubation experiments now, comparing 5, 10, 15, and 20 degrees to understand better how much slower is biochar decomposing at lower temperatures. Also, most of the tests are rather short, about 1 year. Many also are 2 years. And most of these biochars have not been analyzed with these more advanced methods. So the actual detailed characteristics of the biochars are not known. But I said that this is the most established methods, and I've shown now some of the data that has been experimentally developed. But also over the years, these data have been used to develop methods for understanding biochar stability over time. First one was in 2010, another one in 2013. This one established HC ratio as a key characteristic of biochar, and also biochar, how much biochar carbon remains after 100 years as the time frame for studying this. This has continued with in 2019. This model was introduced into the IPCC methods for national greenhouse gas inventory, so it's possible to include biochar in national climate reporting since then. This one uses pyrolysis temperature, and the F-perm here is another name for the fraction of the biochar carbon remaining after 100 years. And that same research group published a paper a couple of years later with some minor modifications of the same model, with the temperature and the HC ratio as two indicators then of the biochar persistence. And we can see here, even though there is a straight line, there's quite a number of dots that don't fit perfectly well to these linear regression. The R square is 0.33, which will some of you will be able to interpret, but it's not super great correlation, but rather work in process. This is how much we know in 2021. And in our paper, we take this one step further. This curve that I show here, it's not in the paper. It's what we actually recommend for use. And I will describe it a bit how and why. So this one also still uses BC100, since that's the well-established metric. But we have published at 7 degrees soil temperature because that's the average temperature in Sweden, which is our focus. We are correlating to HC ratio because after having looked at all other options, this is what we see as so far still the best to correlate with. And biochars produced at high temperature will be here at the lower end. Biochars produced at lower temperatures somewhere here, 0.6, maybe up to 0.9. And when we move beyond to these lower values, these are not biochars, but biomass that is expected to decompose fully in 100 years. And here you will see fewer dots than in the previous one, and that's because we've done a detailed analysis on which samples to include. And in our scientific paper, we explain in detail what samples we include and exclude and why. And this curve is what we think we can recommend for anybody who needs information now, but we don't expect this to last for very long. So there's really a lot of research going on, and we're not done yet in terms of knowing the long-term stability of biochar. But the report that is here, and what's also included in the invitation to the seminar, this tries to explain many of the things that I have said today, and in particular also how we came up to this being our recommended model. Then I would like to reflect a bit about the 100-year durability. It's become, in the biochar research, the established metric, this BC100, proportion of biochar remaining in storage after 100 years. And that is perhaps mainly because 100 years is a nice number. It's also somehow at the very end on how long can you stretch these extrapolation. The experiments are for a few years, and we can sort of safely extrapolate a bit beyond that, but already when we are at 100 years, it's a bit shaky. That's becoming more of a problem because there's more and more interest in the even longer term, not just 100 years, but longer time cycles. And I'll come back to why, but first just give an answer then to what do we know. We cannot really quantitatively model when we go beyond 100 years, but we can say some things anyway. The biochar is not suddenly going to start to be degraded quickly. So it will be slower and slower. So if a lot remains after 100 years, then a lot will remain also after several hundreds of years, up to 1,000 years. So for policy and for climate impact, 100 years is not a set the interesting time frame, but rather we have both shorter and longer time frames that are relevant. And that for the shorter time frames, that's that we are actually already experiencing the climate crisis, and the atmospheric concentrations matter to reduce, to stop increase, and then first establish to stop the increase of CO2, to reduce the emissions of CO2. That's crucial also in very short term. And just like growing trees removes carbon from the atmosphere, and that is relevant in climate policy, that tells us also that biochar storing carbon here and now and for a short term is also relevant for the climate. But the longer time period is relevant because fossil carbon dioxide emitted, remains in the atmosphere for much more than 100 years. It's not gone after 100 years. And that means that if we want to use carbon dioxide removal and biochar to offset fossil carbon dioxide emissions, then we need to look at longer time periods beyond 100 years. And this is an important driver for many in the voluntary market, and that is where money is right now and going into carbon dioxide removal, and that makes it very relevant from a market perspective. But for climate policy, both are relevant, but they're not equivalent. Longer storage is better, so it's definitely meaningful to have higher, to set a higher price on carbon dioxide for longer carbon storage periods. And I'd like to say a few words about this question. If biochar inertinite is inert, because there's been a lot of promotion of this stating that it is indeed inert, and we can expect biochar to remain in the atmosphere, to remain in the soils and treat it as permanent. My short answer is that I don't know. There is definitely reasons to believe that we can consider these inertinite fractions of biochar as being very persistent, but we don't know yet enough about how this behaves in the very long term. The research that I have been presenting and know about can't really say us so much about the very long time perspective. So here is a need for other methods to come in, but also to integrate the understanding from soil science and the processes going on there with the understanding of what has happened on geological timescales, which is not directly translatable to placing biochar in soils. And this brings me to a few reflections about the science and policy processes I'd like to share with you. The policymakers and market actors, they need useful and reliable answers to the question, how long is the carbon stored in biochar? But these are complex scientific questions. Research is still early and very much ongoing. Research is presenting and sharing this evolving knowledge. And then this is used in the policy process and market development. And these arenas are different and speak different languages. And in research, remaining uncertainty is a driver for more research. It's where we become interested, want to know more, want to look further, and we see that as natural and inevitable, that we don't know everything, but we will learn more as science progresses. But in the policy and business arena, any remaining uncertainty is a risk factor, and it's a cause for delay of development. So there's a need in that area to establish what we actually know, and to use a language of a highest certainty than a scientist is comfortable with, because in the scientific arena you cannot seriously be so sure about things, but rather to stay open-minded and try to understand better is how science evolves. But that doesn't mean that we should just spread all the scientific uncertainty into the field of policy and market, because then we would be causing delay that is not necessary. But we're struggling with this, we're working on it, and one way that we have done such work is a process that we had in the middle of last year. So before finishing our research, before the Research on inertinite was published. We, Elias, Asi and I, brought together a large team of scientists, and we developed this statement. The full statement is available, but I've extracted this citation. That there is a clear consensus that biochar produced and used following best practice is a relevant climate change mitigation option. Long-term carbon storage in biochar is one of several reasons for this. And the remaining uncertainty about the durability of biochar carbon storage should not delay support for biochar development and deployment in practice. And that is because of the reasons that I have shared here before, that we do need biochar as a climate mitigation tool. And there is no reason. We know enough about the durability of biochar to be able to say that this is a good carbon dioxide removal method. Looking ahead for the future, there is a lot of research, different groups working on different aspects, such as advanced biochar characterization and linking, knowing more about the biochar itself to the laboratory and field incubations where we measure what happens with the biochar in soil. Also effects of soil conditions, looking more into effects of soil temperature, moisture, biological activity, and also understanding of biochar particle transports in field conditions. And that's the end of my presentation. Now I look forward to answering your questions. It's not just me. I have a great team that I've worked with. I've mentioned Elias and Hai Chao before. We also have Erik Karltun and Harald Sedelund, who are researchers at SLU. And then we have 2050, the company, Helena Söderqvist and Tom Kjellgren, who have also been part of developing our guidelines report and the communications from the project. So I would like to thank you all for listening, and also just thank the team in the project for all the work. And here are also some links. I hope you're very welcome to look deeper into our materials and to contact us. Thank you very much.
Thank you, Cecilia. We have about 10 minutes and we have a few questions coming in that I feel will take some time to answer, but I try to select them a little bit. There's a very long one that I will have to read out loud. It comes from Ring, and he says that he has a question considering the Hanei study that you mentioned in your presentation. He says that his problem with that study is the inference that because investigated or higher rank coal is ancient, mostly because it was buried, and has high reflectance, that everything with a high reflectance must be old. I do not question that anthracite and high temperature biochar is thermochemically stable and should degrade slow, but claiming full inertia goes too far. Certain microbes can degrade even graphite. What is your take on this?
Yes, so this is not my expertise, but I'm reading and listening, and I do see, so I'm not going to argue against that. I think these are reasonable
points.
points.
Okay, I think another interesting question comes from Aum, who says, thanks you for the great presentation and your efforts. He says he has been working on making biochar with over 400 smallholder farmers in Africa. And he asks, how do we measure H2C ratio if the lab is not available in country? Is there any methodology to do the tests on site? Or what are the alternatives?
No, as far as I know, these are tests that require laboratories. So I don't have anything to offer straight that could be done under field conditions.
Maybe temperature measurements are easier in a situation like that, and maybe we can say there is kind of a strong correlation between the maximum temperature and the H2C ratio. So there is a safe zone, let's say, of temperature that then can guarantee a low enough H2C ratio. So maybe temperature is the easiest to measure, right?
That's a good point. Yes.
Okay, then we have Ansjorg asking, thanking you a lot for the great overview. We know that the state-of-the-art industrial biochar contains 0.5 to 3.5% of labile fraction. So what can we really draw from incubation experiments?
Yeah. So what we mainly see is that labile fraction degrading. And that means that we know less about what happens with more stable fractions. That's the short answer. So, yeah.
Yeah, sorry, I need a second to read the questions.
Yeah, no, that's fine. I could also add that working with the incubations and this type of methods, it's not that it's perfect. It's and the longer we are interested in beyond 100 years, the less relevant these methods become. We're extrapolating from short-term impacts or what happens in the short term, and the longer we want to understand, the less these methods will be of relevance, and we need to combine with other types of methods. And I do think that understanding in detail how biochar is composed is crucial.
There is a question from Hamed Sanei, and he says that the current decay model results in 0% carbon remaining after 1,000 years for all biochar in respective of their H2C ratios. This doesn't explain abundant existence of char in archaeology and earth system longer than 1,000 years. Why the model doesn't agree with the basic natural observations? Could it be wrong? Can I can maybe just before I leave the word to you, Cecilia, I can say that of course it can be wrong. I think that any scientific model could be wrong. So this is a model, so that's kind of intrinsic, but please.
Yeah, no, I don't know what model is referred to here that would give 0 after 1,000 years, because that's not what our models show. We say that we have often up to 90% after 100 years, and then you will not have 0 after 1,000 years. But we are not extrapolating and giving numbers at 1,000 years, because we don't think that we have that it's meaningful to extrapolate like that from these models.
Okay, I'm looking now also into the chat where there are also a lot of questions, and Christian is asking what differs between geological inertness and storing inertinite in soil?
Yeah, so main difference is the environment. And I'm not into geology, but most of that material is deep under the ground. Whereas when we're talking about soils, we have material that is exposed to a lot of biological life, vegetation, microorganisms, and also the weather, temperature changing, moisture changing, things like that. So it's environmental conditions that is the main difference.
Yes. Maybe I can add a question. I don't know, but then could it make sense to then test geological samples in the conditions where biochar is applied to verify how if there is any difference in their behavior? I don't know. Maybe someone is already doing that.
Yeah, no, I think that is perfectly sensible to do that kind of experiments. Yes.
Okay, I can move on to another question. Stephen is asking, I was wondering about your thoughts and opinions on the European Biochar certificate that biochar makers can apply to register their product as verified CO2 sequestration.
Yeah. In brief, I'm very critical to the whole starting point of the policy, and therefore I'm not willing to discuss the details of it. But we are sharing our knowledge and trying to support anyway the ongoing process, both different actors in that process to share the knowledge. But I'm not in favor of the approach as such.
There is another question from Michael, which I think is interesting. I wonder if you have considered the carbon losses during biochar creation or production. I have the impression that hotter pyrolysis temperatures that are needed to create the most stable biochars also release the most carbon during pyrolysis. How this should be considered?
This is correct. When you expose biomass to higher temperature, larger proportion of what you had original carbon will be emitted as carbon dioxide. So the biochar carbon remaining when the biochar is new is less than if you would produce it at a lower temperature. And this is something to consider in the whole balance of how to best use a certain amount of biomass. That's expanding the discussion a bit further from what I have discussed today.
Yes. There is also another question that maybe drifts away a bit from stability, but Gabriella is wondering if about the transport of biochar, knowing that it can absorb pollutants. Are we worried that biochar will be an accidental hotspot for releasing stored pollutants over time?
Stored pollutants. That's what you are investigating in your research, right, Julia?
Yeah, that's a bit a different field.
Yeah, it's really beyond what I have expertise, so I'd rather not go into that.
And it's really a complex topic when it comes. It also depends which pollutants we're talking about. So maybe we leave this for another webinar.
I could say that if this had been a large risk for all kinds of biochars, we would have known more already, because then there would have been more research into this. But that is not a scientific statement, but rather a sort of based on my understanding how science and scientists work.
Okay, I think I've gone through all of the questions. No, wait, maybe there's something new popping up in the Q&A. Esben from Copenhagen University. He is working with incubation studies with straw and biogas fiber biochar pellets. both with H2C org ratios of 0.3, but with very different CO2 evolutions at 20 degrees. Biogas fiber biochar has double rates CO2 compared to straw-based biochar still after 1 year. It seems that manure-based biochars decompose faster in the short term than straw and wood-based biochars, even with the same H2C ratio. What is your explanation for that?
Very interesting. And we need more such research to understand these things better. Very briefly, first, I should say it's not my expertise, so I'm not giving a definitive answer here, but straw and wood, there you have the woody structure, the lignocellulosic structure is there, and then you pyrolyze, so you sort of fix that through pyrolysis. When it's manure or digestate, it's been through degradation processes, intensive microbial degradation processes. So you have a lot more of the carbon in other forms. And that could be a reason then that what is formed during pyrolysis is also less stable. But that's just a tentative answer.
Yes. Good. I think we have run out of time. So I hope we managed to answer most of the questions. Thank you, everybody, for participating to the webinar today. And thank you very much, Cecilia. Yeah, I think this discussion will go on. And of course, also research will have to move on, and we'll learn more. Thank you very much. Have a good weekend and a good Easter. And yeah, see you again soon, I hope.
Thank you.
Bye-bye.
Bye.